there are irregular types of linear programming that you should know. If you know them, you can handle them. In fact, as part of your thesis or dissertations or PhD, you can extend these irregular types of linear programming. Irregular types, which means they are not regular. They are not like the usual one. Now, what makes them irregular? And why are they interesting to look at? Well, one of the things that makes them irregular is that they do not have the same style of solutions like the normal linear programming problems. So for the usual ones, there are some rules. There are some rules. For example, we have rules like the optimal solution should be only one. So we are always looking for feasible solution points. Feasible solution point. So we want the optimal solution to be only one. And then we also want a situation where the feasible solution area is closed. It's closed. But there are some situations that it's not closed. When I say it's closed, it looks like, and there are 4 different types of these irregular linear programs. We're going to look at them. The first one is multiple optimal solution. Multiple optimal solution happens when the solution to the linear programming problem is many. Now, in the Farmville Ghana Limited, what were the solutions? How many solutions did you have? How many optimal points did you have? Anybody? Now the questions are open. Oh, let me do it today. So I'll be calling everybody on the call by going through all. So let me start with you, Simon.
So for the Farmville Limited, there were 2.
How many was the optimal solution?
Optimal solution.
Yeah. How many were the optimal solution point?
The points were 3.
There can be points. I said optimal. Listen to the English. Optimal solution point. Those ones were not solution points. They were not optimal. How many? Solomon?
There were 2.
There were not 2. Albert?
Sir, please, I missed that part of the class.
You missed that part of the class. Chris?
Yes, no, it's 1.
1. What were the values of that optimal solution point? Eugene? Eugene?
Yes, Doc.
Pay attention, everybody. Yes. What were the coordinates?
The coordinates were 2 and 5.
That is wrong. Jerry?
Doc, I think 8 and 24, or 24 and 8.
24.
24 and 8.
You see, somebody just mentioned now it has, you've remembered it, 24 and 8.
I was quite confused because
you cannot be confused in my class. Opelech cafe.
We use the 2 lines.
You cannot be confused. You've gone through this thing 3 times. You can't be confused. The word optimal solution point is a point made up of multiple coordinates. X1, X2, X3, X4, X5. It's a point or a surface. So understand that when I say optimal solution point, you should mention the coordinates there. Now, in that optimal solution point, the coordinates were 24 and 8. And that 24 and 8 provided us with just 1 point. And it was a solution. But then in multiple optimal solution, the solution point is not just one point, but multiple points. And you're going to see an example here. For you to know that the solutions are multiple, you would have to identify the ISO profit line or the ISO cost line. ISO profit if it is a maximization, or ISO cost if it is a minimization. I'm going to give you an example for all of you to work now. So be ready. Are you with me? An example of the multiple optimal solution LP. That is what I want you to start thinking about. An example of the multiple optimal solution LP. Okay, so let's take an example of a linear programming problem, which will have a multiple optimal solution, how it happened. Now, why would there even be an optimal solution point that is alternate? Another word for the multiple is alternate. The alternate means that there are several alternative solution points. This will normally happen when a manager quotes something different from what a production manager will say, or what a marketing manager will say is quoted differently from what a financial manager will say in the same company. So all of them will keep different ideas, and that will lead to multiple optimal solutions. So let's take an example of this. This is a linear programming problem you see on your screen. This linear programming that you see on your screen, if you want to find the optimal solution point, what is the first thing you got to do? If you want to find a solution, what is the first thing you have to do?
Doc, can I try it?
Yeah.
You equate the various constraints to 0.
You equate what? No, the first thing you got to do, the first thing. I want the first thing to do before you start equating things to 0. Albert.
So you write the objective function.
No, you don't write objective function. Emily.
But my first step would have been what Jerry said, like getting the graph ready. So
yeah, but my question is, how do you get a graph ready? That's the first thing I'm asking.
Okay.
How do you get a graph ready? What do you do first?
Okay, so Doc, I'll use the constraints for the graph.
Which constraint will you start with?
Doc, the first one, the resource constraint.
No, you cannot start with the first one. All of you, when you're writing a linear program, you always start with the negativity constraint.
The non-negativity constraint.
If you don't get it right, you will miss it wrong. Write it down. Everyone, write it down. You are not here to learn. Guys, you are here to learn to teach. I keep saying it. If you don't learn it well, you can't teach it well, you will mess up. Simon, what did I say? What is the first thing you got to do when you're drawing linear programming graphs?
So you draw the graph.
You don't draw the graph, Massa. Are you here at all? What is the first thing you do?
So you find the coordinates for the graph.
What is the first thing? I just said it 4 times. Albert.
So you said the non-negativity function is the first thing.
That's that what? Non-negativity function has done what?
It sets the frame forward with the graph that will be plotting within.
So the first thing you do is to draw the non-negativity constraint. Write it down, everybody. Write it down. You see, you didn't write it down the last time you met. That's what the problem is. The problem is that you find laziness when you are typing things down so that next time you can refer to it. And so when subsequent times comes, then you're now changing the chorus. So you draw the non-negativity constraint. That is the first thing you do. And how do you draw the non-negativity constraint? You draw it with these lines. You write your x1 and then you write your x2. This is a non-negativity constraint. It is after that that you draw the other constraint in order of which one is the easiest. So normally you don't draw the most difficult constraint first. You draw the constraints in order of the easiest. Now here we have two constraints, a constraint 1 and constraint 2. Which one do we draw first? 1 or 2?
2 first.
2 first.
2.
Now how do you draw the constraint 2? Chris Duncan. How do you draw constraint 2?
So now you equate the equation to 0.
How do I
find the
equation to 0? How do I equate the equation to
find the coordinate?
So how do I do it? How do I do it right here? I knew he wasn't paying attention. That's why I called him. Eugene Mali.
Yes, Doc.
How do you draw the equation 2? How would it look like
if I set the value of x1 to be equal to 3, then I can substitute that as x1 equals 3, and then the
so how would I
x2
draw
be
it?
there.
How would the drawing look like?
So it will be on the x1 axis.
And how will it
So
look?
3. It will be a point on the x1, like x.
Okay, so a point, and I call it what?
You call it 3, 0.
3. And then?
Yeah, the 0 for that is on that plane. It's at the origin, so it's 3, 0. That's
right.
all. That's the point.
So how will I draw the line?
So for this, there wouldn't be a line because it's occurring at that point.
There will be a line.
There will be a line.
Jerry, how would I?
No, please, you draw a power line to the x2 as it's passing through 3.
Exactly. So you draw a line. You see, you guys say you learn things. So that is how you identify the x equals to 3. Don't say yes. You have to learn. Write it down. Take notes. You're listening. You're only watching and listening. Nothing else. No note taking. That is where the problem has always been. Learning is a skill. If you don't have the skill of learning, you will learn and learn and learn, and you will not understand it. You will not be working because you are not learning the right way. If you know the sort of question, for example, you're going to do in your midterm exam, you will be learning. You'll be learning. Okay, so this is a constraint for the constraint 2. That is how you draw the constraint 2. And you can see that I've labeled it. But you're supposed to shade it. After labeling, you're supposed to shade it. You use the equality symbol to do it. But now we want to shade it. How would the shading be?
We'll shade it towards the left-hand side.
Left-hand side?
Less than or equal to 3.
Left,
towards the
what?
The
Yes.
left hand, towards the since x is less than or equal to 3, the shaded region will go towards the origin.
So you should say left-hand side of x3. That's what you say.
Okay.
When you say left-hand side, this one too is a left-hand side of x2 area. So when you say left-hand side, you have to be specific. So you shade it, the left-hand side of the X3 vertical line. So this is the area for that. So when you do that, you can now change this sign to less than or equal to, meaning that the area plus the red vertical line together make up the constraint. Then you draw the next constraint, which is constraint 1. That is the only constraint that is left. Now, if you divide both sides by 2, okay, you can get two different things. So you can divide both sides by 2 here, and you get 3x1 plus 2x2, okay, set it to equal to 12, and then run it. So if x2 is 0, x1 is what?
6.
Oh,
It'll be 4.
Somebody mentioned 6. The person just...
No. I saw the figure as 12. Sorry.
If x1 is 0, what is x2?
6.
So you now plot these two. Okay, so x1 is 4 and then 0. That will be here. Okay. And then x2 is 6. That will be somewhere there. Yeah, Jerry.
Doc, please, sorry to take you back. The line that is passing to the 3, because we are sailing towards the 0, I don't know if I heard it right. Do we take away, when we are rewriting, do we take away the equal to sign? Or it should still be less than equal to 3?
It's still less than or equal to 3 because it includes the red line.
Okay.
There's a red line that is equal to part. And then the less than part is the blue line.
Okay. Thank you.
So once you've done this, you join these two. And once you've joined the two, you can label this axis as 6x1 plus 4x2. You do all of these, 4x2 less than or equal to 24. And now you have to shade this particular area. And the area is this section, all of this section. You are shading the area common to this second constraint. I mean, area to this first constraint alone. So now we've shaded the two areas. We now need to find the common area. And as you can see, the common area obviously is going to be this corner here. Okay, this corner here. Not that side. Not this side. It's not this side. And so we now have a point here. Okay. And then we have another point there. And then we have another point here. We are going to prove why this is a multiple optimal solution. In fact, you wouldn't know what it is in an exam, so you have to now draw and calculate before you can prove. So how do you get a multiple optimal? How do you get the solution? Well, one way to get a solution is to get a corner point. As you can see, the corner points are 3. At this section here, we have 3 and 0. Okay, substitute that into the z function. 3. Okay, so this one is 3 here, and then x2 is 0. So we are going to have z equals to 15. Is this a minimization?
Yes,
yeah.
minimization.
Yes, it's a
This is not a maximization. This is not a maximization, it's a minimization. So everything is not correct. So if it's a minimization, you have to wipe off all of this. So this shaded area don't work here. What you need is that. It's a minimization. So you're looking for the minimum cost. So here you rather shade here. But the thing says minimum. It's correct. It's actually correct. I don't know why I changed it. It's correct. So we substitute it and find the lowest cost. So let's first take the 3 and 0. Substitute the 3 and 0 here. It means that the Z value for the 3 and 0 is going to be 15. Okay. To be honest, believe me, this thing is not supposed to be a minimization. I think it's a typo. It's supposed to be a maximization. So keep it in mind, it's supposed to be a maximization. Then the next thing is to go to this corner point. If you look at this corner point, the value here is already 3 there for the x1.
Please, the x1 that you just calculated, is it 3 or 5? I think it's 3. You did for 0, 3.
Yes, it's 3, 0.
So that makes it 9. You said 15.
Ah, yeah, it's true. So this one is 3 by 3, which is 9. It's true, correct. And then you do the next one, and the next one here, you get 3 there, and then the y axis. The way to get a y-axis is to substitute this 3 into the next function here. So that is here, you substitute the 3 there. So that is 6 times 3, 18. So once you get the 18, move the 18 to the right-hand side, and you'll get 24 minus 18, which is 6. And then you divide both sides by 4. So you're going to get 4x2 equal to 6. Which means that x2 is what? 1.5? Is it 1.5?
Yes.
Yes. So x2 will be 1.5 here. So at this corner point, let's call it corner point B, this corner point A, that corner point C. So at the corner point B, you have the coordinates to be 3 and 1.5. So let's substitute again. So 3 here will give you 9. Then 1.5 will be here, multiplying the 2. 1.5 times 2 will give you 3. You add a 3 to the 9. That gives you 12. So at this corner point here, you have 12. So Z is actually 12 for that. Remember, the other one, Z was 9. Okay, so profit was very, very low at that point. Remember, like I said, this is a maximization instead of the minimization rating. Now, let's go to the next corner point here. This is the interesting part here. The next corner point is 0 and 6. X1 is 0. X2 is 6. Substitute them. What do you get for Z? At the corner point C.
12.
You should also get 12. So what does that mean? That means that anything between B and C is what? Solomon. Simon.
Yes, Doc.
Anything between B and C is what?
The optimal solution.
Optimal.
And the profit between B and C is what?
Maximum.
There will be 4.
I want the value.
That is 12.
Good. So you get 12 at any point between this. So that's what we mean by multiple optima. So the value between these two, if you substitute these two values between that, they will give you 12. Each value. Okay, the first one is going to be 3 and then 1.5. The next one may be something and then 1 point something. The last one will be 0 and 6. All of them are going to give you the same thing. So every point between B and C is going to give you a solution that is a maximum solution, which then goes contrary to the single solution we're looking for. Therefore, we have alternate or multiple optimal solution. Now, in this case, we were fortunate, okay, not to calculate from the rest. You just calculated the C and just calculated, and it got the two possibilities. And you can now deduce that between the two of them, there are multiple optimal solutions. That is what this situation is. So this is a typical example of a multiple optimal solution. Now, if I show you the others, your job is to be able to identify which one of them is a multiple optimal solution. But that is it. That is the definition of a multiple, and that is how you demonstrate it. Another way of showing, and these are multiple choice questions, another way of proving that something is a multiple optimal solution is when the isoprofit line is tangent to one of the constraints. Write it down. When the isoprofit line is tangent to one of the constraints. So if you look here, the constraint from AB is, we use BC now by the same thing. The constraint between A and B here, if we try to draw the isoprofit line, the isoprofit line is this one. How do you draw this line? It's simple. Just do 3x1 plus 2x2 and then equate it to any number, any reasonable number. Okay, I normally like to equate it to any reasonable number. Let's say equate it to 24. All right. And then ask yourself, if x2 is 0, what is x1? If x2 is 0, x1 is what? Is it 8 or 7?
8. 8.
Good. X1 is 8. And if x1 is 0, x2 is what? 12. Okay. So watch out. We are going to plot 8 and 12. That's what it means. And when you go and plot 8 and 12 on your line, watch it. 8 is going to be somewhere here. If we were to plot, 8 is going to be somewhere here. And 12 is going to be somewhere there. You plot these two, you get a line. If you start shifting that line down, okay? If you like take a smaller number, because this one has gone higher. So let's reduce the 24. Okay? Let's cancel this 24 and make it like
8.
6. Okay. So if you make it like 6, if x2 is 0, x1 is what? 2. So now we are here. And if x1 is 0, x2 is what? 3. So now we are here. So when you join these two, you can see once again, this line is parallel to the constraint line here. This is an isoprofit line. And then this very one, when it went too high, is also parallel to the constraint line. That immediately should tell you that we are dealing with a multiple optimal solution. That's a clue. That's a clue. If you like, double this. Okay, if you double this one, 2, you'll get to the 4. And if you double the 3, you get to the 6. So that means that they are parallel. And the moment you get that parallelism, it means that you are dealing with infinite optimal solution. The same as alternate optimal solution or multiple optimal solution. Okay. Any question on that? The next one, so you should be able to distinguish this one from the one we're about to look at. The next irregular, strange one. Okay. Everything I did is here, so you can check it. And by the way, one way to solve the multiple optimal solution is if you don't want, I like the multiple optimal solution because an advantage of it is that it can help you to be able to know the different quantities you want to produce. Because on that line, you have the option of producing anything here. You can produce 0 and 6 here. Okay. You can also produce 3 and 1.5 here. So you have the option to do whatever you like as a manager. But if you want a single solution, then you can use Go programming. You do Go programming next semester. Use Go programming, and you can use Go programming to solve the thing and get your one-time solution. The next one. The next strange linear programming problem is known as infeasibility. As the name sounds, infeasibility, and this goes to you, Emily, because you've been learning a lot from DEA, but you have not learned infeasibility technically from the linear programming balance itself. Infeasibility means there is no solution to the linear programming. Cool. Stop. What do we mean by there is no solution? So when there is a solution, what it means is that the constraints, are satisfied, or at least one of the constraints is satisfied. For example, if you guys can remember the Farmer Ghana Limited, you could see that in one of the constraint was binding. But in another one, it wasn't binding. But in one of the corner points, the two constraints were all binding. In fact, the point B, you could see that they were fully utilizing all the resources. Do you remember? I'm speaking in abstract terms, but I know you guys remember.
Yes, Doc.
So the constraint, at least we satisfy the constraint. In an infeasibility, there are conflicting constraints. One constraint is saying that this value is below. Another constraint is saying that this value is above. So it's like you go your way, let me go my way. Let's take a mathematical example. So normally you want the constraints to intersect, but they don't intersect. At least one constraint should intersect another. I don't mean that this constraint should intersect this, and this one should intersect both of them, and this one should intersect. No, no, no. You can intersect some and not intersect others, fine, but at least you must intersect somebody. But when you have a constraint that constraint is sitting on its own, he is not intersecting with anybody, straight away, we have a problem of infeasibility. Let's take an example. An example of an infeasibility is this. And again, this is where we talk about a marketing and a production manager are giving different, different decisions leading to some wrong outcomes. And one of them will have to revise the constraint, but the person doesn't want to revise the constraint. So let's take an example here. So this is the Z function, which we are maximizing. And this is our usual non-negativity constraint. Look at this constraint. If I had not drawn this, which normally I wouldn't draw, you should be able to draw this. And look at this one, X1. X1 says everything that is above 4, including 4, should be shaded. So when it comes to X1, the shading of the X1 is going to be everything here, okay, above 4. Okay, X2 says that everything above 6. So X2 is everything above 6, but it is X2, not X1. So this is above 6. Everything above 6 is what we are shading. That's what X2 is looking for. So you can see that just between these two, let me delete this. Just between, just between these two alone, you can see that here should have been our optimal solution area. But then you come to this constraint, the problem child. This constraint says that if X2 is 0, X1 is 2, isn't it? Okay, so that's here. And then it says if X1 is 0, X2 is 4. Okay, so that's here. This constraint is not intersecting with any of the other two. So it has created another feasible solution area. Once we have kind of two different areas, we have no solution. So in DEA, for those of you who will be looking at linear programming envelopment analytics, you will notice that this guy is outside. Any point here, point A, is outside the original feasible solution area here. It's outside. And because it's outside, it is not feasible. It is not feasible. And this happens when one constraint, you don't need even two constraints to violate. When one constraint is violating all the laws or the rules of engagement. Now, how would you do this without drawing? There is no, yes, you can use computer to quickly tell, but how would you do this without drawing? Who can tell me? It's possible to do this without drawing, by the way. Without drawing, you should still be able to dictate. How will you do that? Well, you check the sign. The signs will guide you. You see, this one is less than or equal to, and these ones are greater than. So you ask yourself, whatever I find here, watch it. This guy is saying that, this guy says the minimum value is 4, okay? That's what X1 is saying. So I can put that here. Minimum value is 4. And this one says the maximum value is what? Is 6. So I can drop that here. So at the left side, you have 4 times 4, giving you 16. And then the X2, you have 2 times 6, giving you 12. So you have 12 plus 6, giving you what? 28. And that 28 is supposed to be less than the 8, isn't it? But as you can see, you have the 8 here, and this would have been 28. It's supposed to be less than. It violates the inequality term. So straight away, you know that there is an infeasibility there. It can be tricky when we come to the subsequent ones we are going to talk about called redundancy. Okay. But I want you to know that even without drawing, you should detect it. Okay.
Doc.
Yeah.
Can I ask a question, please?
Of course. Ask.
Yes. With this example that you just gave, what if the 4x plus 2x less than or equal to 8 line, the values are such that it goes beyond the intercept of x4 and then x6?
It goes,
and it's coming down.
Say that again. What you mean by it goes beyond the intercept?
So let's say the line x4 plus 2x is equal to 8. It's somewhere, let's say the 2 is at say 12, and then the 4 is at say 12, and we have the line up there. And you draw the distance, you still have the shaded area intersecting within the yes, something like that.
You have it, then there is no problem of infeasibility. There is no irregularity. We're back to our normal linear program.
Okay.
Yeah, it means there's a solution. So suppose that line is like this, then we'll get the corner point now here and here. So this becomes our feasible solution area. So we'll now find the answers to the point.
Thank you.
Any other question?
Yes, Prof. Please, I have a question. In the earlier example that you gave, where we're seeing the isoprofit line tangent to the optimal solution, we could see that all the lines are parallel and they are not meeting at any point except for the axis for the x1 and then the x2 axis. In that situation where there is none of them intersecting each other, can we also say there is an infeasibility in the case of this?
They are not intersecting each other.
Yes, please. There was no point where either of them.
Let's go and then you share the return. Yeah.
Yeah. Yes, please. Yes.
Explain.
The two lines, the A and then the B, and then okay. Let me use the point 6, 4, and then the 4, 3 are parallel to each other.
Not constraint. The 4, 3 is an isoprofit line. It's not a constraint. The infeasibility we are talking about is when a constraint and another constraint, okay, a constraint and another constraint. But this is an isoprofit we're trying to draw to show.
All right, thank you.
Guys, it's important that you understand these things by asking questions, because when I put the mathematics down and you have 5 equations, one is infeasibility, one is this, one is that, you should be able to note which one is and which one is not. Okay, let's go to another infeasibility. This is a tricky infeasibility, but there's also redundancy in it. So we said that if you look at this one here, this is a constraint. The one you see vertical here is a constraint. And there's this third constraint, apart from these two would have created a beautiful solution area, as you can see. And then we would have gotten the results to be at this corner point, and this vertex. And it would have been done. But then there was a third constraint that came into the picture. And this third constraint says that the feasible solution area should rather be here. So you can see that this guy is not intersecting with any other constraint. So Somebody will say that, but can't we stretch it down here and then it will intersect with this one? What will it violate? If you stretch it down and it intersects with this one, what will it violate?
The non-negativity rule.
Exactly. The non-negativity assumption will be violated. So we can't stretch it further. And therefore, this constraint here, because it's not intersecting with anyone, it creates infeasibility. The word infeasibility here is created an infeasible solution. But also, it has also created another thing called redundancy. It's created another thing known as redundancy. Why? Because I can delete this and still be able to use this left here to do my work. So it means that whatever is here in this constraint is redundant or superfluous. It shouldn't have come. It's not needed. You can still use this one to do. So we can consider this constraint as a redundant constraint. But if it is necessary, then it has brought about infeasibility. Any question? Okay. So let's go to another. I mean, sometimes you usually see graphs rather, okay, but sometimes I would like to use mathematics.
Doc,
Yeah.
please, in the redundancy, in a layman's language, can we say that because that constraint is standing alone and by shading it's not interacting with any of the others?
Yes, that's why it's redundant.
Okay, thank you.
Yeah, superfluous. Let's go to unboundedness. I asked you a question that when the linear programming is unbounded, let's put it this way. Every linear programming has a primal model and a dual. When the linear programming, the primal model is infeasible, then the dual is unbounded. That was a question I was asking. Yes, Emily.
Please, to the infeasible, does that mean that all infeasible are redundant?
No,
Since
no.
they are going to be constraints.
No, not necessarily. Not necessarily, because if you are infeasible, I have not declared it as redundant. So because I have not declared it as redundant, it doesn't make it redundant. The fact that it's infeasible means that it has brought about a problem. You cannot say that let's ignore it. But the moment you say let's ignore that constraint, what if? So look at this one here. If you take this one here, you will notice that this one has brought about infeasibility. And it might look like it is redundant, but we can't declare it as redundant. Why? Because if it is infeasible, what if it is needed? What if it is needed? What if this constraint is an important constraint from the CEO of the company based on some restrictions he gave that brought about this line? And you tell him that let's throw your knowledge away. He said, no, this is innovative. You can't throw it away. So you can't make it redundant. That way you can't throw it away means you can't make it redundant. Okay. So redundancy is a decision to make to declare a constraint redundant. And some of the constraints are, you cannot forgo them. You can't. You know, for example, some things are necessary evil. You gave birth to a child. The child is deformed. The child is blind. The child cannot hear, cannot see, cannot walk, everything. You say, I'm going to kill the child. No, you can't throw it away. So there are certain situations you got to deal with it. You got to handle it as and when it comes. And so you cannot make it redundant. So that is the relationship between the two. Now let's go to the last but one, unboundedness. Now watch the infeasibility. Do you remember what we said about infeasibility? Infeasibility is when there is no solution. That's infeasibility. When there is no solution to the linear programming problem. Unboundedness is when the feasible solution area is open. When it is open, It's like the opposite of infeasibility. Now remember, we have multiple solutions. Do you remember? 2, 3, 4, 5. And then at the extreme lower level, we have infeasibility, no solution. Then at the opposite section of the no solution is many solutions, or better still, infinite solution. The normal linear programming has a finite solution. One solution, one solution, finite. But sometimes you will have a solution that is infinite, infinity, infinite solution. And that happens when the feasible solution area is open. And when it is open, there's no point. Okay, there's no point. And because there's no point, nobody will be able to what? To actually be part of it. A typical example will make it work. Now, when would that happen in the first place? Okay, for example, unlimited, I say infinite. Unlimited profit is not possible. Unlimited cost is not possible too in real world. So when you have that problem, you check your linear programming because you have formulated a wrong model, and therefore you need to correct that model. Let's take an example first before we talk about how to correct it. Now, in a maximization problem, which is what we are looking at, okay, the feasible solution in a maximization problem, the feasible solution will stretch infinitely. It will stretch to the right, okay, and that leads to unboundedness. Watch, the word unbounded means there is no bound. It keeps going, it's open. And this is a typical example. So we have our x1 greater than 4, as you can see here. X1 here is greater than 4, so I've shaded this area. Then x2 is rather less than 2. Okay, it's 2 or less. So that one, what is it saying? X2 is below. So that one we've shaded here. So look at these two. This one is going to the right, and this one is also going down. So to the right, we have the area that is, but we are looking for corner points, don't forget. And we are looking for corner points to the far right. If you can remember this one, okay? The corner points, we want the corner points that are bowed in towards the origin. But these ones are rather bowed out. Okay, you can see that they are popping out of the origin. The arrow shows they are going away from the origin. But this one means they are closed. They are rather closed towards the origin. This one is finite. This one is infinite. That's unboundedness. So if I go and get this, the z function, do you remember that we said that the z function, the last place on the feasible solution area, where as you try to move the z function away from the origin, the last place of the feasible solution area it leaves, that point is the optimal solution point. But if you look at this, I have z function, another z function, another z function. I keep getting, they keep moving, but they are not touching any vertex as they keep going. As they keep going, there is no vertex. There is no corner point they are touching for you to see, because the whole thing is not closed. The feasible solution area is not closed. This is a typical example of unboundedness. Now watch this carefully. So what then is the difference between unboundedness and feasible solution area? What is the difference between unboundedness and infeasibility in linear programming? Who can tell me? Who can guess? Infeasibility and unboundedness.
Doc, I think that the infeasibility, that one gives us no solution.
Yeah.
But the unboundedness is likely to give us infinitely many solutions.
Mm-hmm. So what would you say is a clear difference? in simple terms. You said it, okay? Are they?
One provides a solution, one doesn't.
Sorry?
One provides a solution, the other doesn't.
Yes, so did you say one that provides a solution, the other doesn't? Is that what you said?
That's what he said.
No. But the multiple optimal solution also provides a solution.
Infeasibility doesn't provide an
Anyway, I can't hear him again. So with one, there is no feasible point. With the other, it goes to positive infinity or negative infinity. Okay, it goes to positive infinity or negative. So which one would you like to have? Which one is at least acceptable? Or which one can we accommodate?
The unboundedness.
Are you
That
sure?
one. Look, but the invisible, if there's no solution, then the interest for which you are undertaking the endeavor is maybe is the interest or the purpose. I don't know if there will be any.
The fact that something is not feasible does not mean it is impossible. Infeasibility does not imply impossibility.
Yes.
Yes. Huh? There's a difference.
Yes.
Infeasibility.
Doc, please. The difference between the unbounded and the infeasibility. You said the unbounded has a positive or negative infinity.
Yeah, it goes to positive or negative infinity.
But that of the infeasibility has what?
0.
Is 0.
Yeah.
Okay.
That's why I asked you which one is the. By the way, the unboundedness, when I say positive infinity, that's when you're doing maximization. And when I say negative infinity, that's when you're doing minimization.
No.
It's unboundedness. And then the infeasibility is 0. So that one, no feasible point, no feasible solution. And I was asking you which one is better, which one is dangerous, which one, I don't know, which one?
Which one the one you can easily accommodate is the invisibility.
That's what I'm saying, exactly. Okay, at least you can create a situation of bringing some small values. You can, it's 0, but the other one is infinite. You can't even get there. So, Emily, you remember when you were trying to code some of the things, it was giving you infinite, but we were trying to mistakenly call it infeasible.
Yes, Doc.
And that is because we're doing both minimization and maximization. And when it is maximization, the way it will code the infinite is different from when it is minimization. Anyway, the key point is that both of them are problem children. That's the key. But there's a way around each one of them. It's not for your level. Okay, so that's it. Let's go to the last one. The last one, we've already spoken about it. That's redundancy. Redundancy. It's not really a big problem. Like I said, you can look. I showed you this one before. Some few minutes ago, I showed you one that was like this. Yeah. So we can ignore it. Now, let me tell you something about redundancy. The redundancy I showed you earlier is not really redundancy, and I'm going to explain why. It looks like it's a redundancy, but it's not. Let's go back here. You see where the feasible solution area is going? It's going to the right, isn't it?
Infinity.
It's not redundant, it's true infeasibility. Redundancy is rather coming to the left. So if if this value, you see this value as you see here, it says x1 is greater or equal to 7. That's what this one is saying. But if it was rather x1 less or equal to 7, then you rather shade this area. You get a point? So you have shaded this area, which means that this area is also important. But the thing is that these two have already created an intersection here. So even though this area is also important, it's no longer important. I don't know if you guys understand.
Yes, sir.
So it's no longer
Then
important.
in essence, you'll be using where the point has been created because it will be part of it.
Exactly.
Yeah, you'll find the intersection of all the three, which will still be the same thing.
Exactly. That is why we say that it's redundant. So we can delete this constraint. It's useless. It's superfluous. It doesn't count towards anything. You can safely exit it out of the whole thing. And that is it. But the invisibility is invisible only when it is going the opposite way. So both of them are not intersecting. The invisibility and the redundancy, they are not intersecting. But the thing about the invisibility is that it's going the opposite angle, opposite way of what the feasible solution area is supposed to be. But the redundancy is actually good because, yes, it's a little bit away, but it captures the others. So if you look at this one here, the redundancy here means that the arrow is pointing towards this. It captures all of this, but we just don't need, it's capturing too much. That's the whole point. It doesn't have anything in common, much in common. There are some portions of it that are not that much in common with the feasible region. So a redundant constraint is a constraint that does not affect the feasible solution in any way. Take note of that. It doesn't affect the feasible solution. So you can safely delete it. And this thing creates a, so do not be confused about the feasible solution area. Sorry, about the infeasibility part and that of the redundancy. So that's it. Okay. That is all about the irregular types of linear code. Any question? I'm going to give you one here, then you tell me which one is this. So here I have a Z max formula here. And then this is equal to x1 plus x2, subject to this constraint, x1 plus x2 less than or equal to 4, x1 comma x2 greater than or equal to 0. I want you to tell me this mathematical model you see on your screen. You're going to tell me and explain fully to me whether it is multiple optimal solution, or it is infeasibility, or unboundedness, or redundancy. Let me see the smartest one among you.
With just one constraint.
Yeah, I wanted to make life easy for you. That's how life can be. It can be so easy. You'll get it.
Okay. Doc, can I try?
No, wait. Who else is finished? Somebody doesn't want to finish that for the person with delay until everybody has finished. So I was coming. Solomon, are you here? Jerry, are you here?
Dog,
You
I'm here. Dog, I'm here.
Okay. Eugene, are you done?
Yes, please, I'm here. I'm done.
You're done. Jerry, are you done?
Dog, almost.
Guys, if you're done, type it here. I want to see. Type it privately to me and let me know which one you have selected. If it is multiple optimal solution, just write MOS. If it is infeasibility, just type I. Unboundedness, type U. Redundancy, type R. If it is Lotto 2, type L. I was just looking at some IA questions and I've asked you this question on infeasibility. Okay, so let me see. Albert has sent me his answer. Emily has sent me her answer. Eugene has sent me his answer. One of you got it wrong. Albert, do you think you're right? Eugene?
Yes, Doc.
You think you're right? You've changed your answer, eh?
I've updated it.
I updated it. The update is even more wrong. Not only when you're confused, that's when you bring two things. You know that. Let me see the next one. Solomon, Oparelabi. You are way out of line. Simon, you're also way out of line. So the answers I'm getting clearly shows that some of you have not understood. So the answer is multiple optimal solution. So let me explain why you choose multiple optimal solution. You and Albert are the only correct ones.
Okay, so
I think I got my graph will be correct.
from the constraints, you can see that your
Listen to the answer.
coordinates are going.
Yourselves.
Okay, so from the constraints, you can see that the coordinates you are going to get are going to be 0, 4, and then 4, 0. And so if you draw it on the graph, those are going to be the only 2 points.
So you're going
So
to draw.
when x1, yeah. So if you put them into the z, you are going to get 0 for x1, 4 for x2 for the first one. And that's going to be equal to the second set of coordinates, which will be 4, 0. And so there are two optimal solutions that you can get. So it's going to be the multiple optimal solution.
In between them, you see that there are multiple ones between.
Yes.
For example, so the z value will be what? 4, isn't it?
Yes, Doc.
Guys, the z value will be 4. So even if you count to 2 here and 2 here, That will give you 2 plus 2, 4. So it means that you have
And
another solution
3, 1.
in 3, 1. So there are several solutions. So one of these are redundant. Which constraint was redundant? The constraint was only one. The other one is a non-negativity constraint. Don't look at that. So the only constraint was this. So I don't know which constraint was redundant for you, Solomon. Or it was Eugene who said that.
Yeah, I did. I think when I plotted the graph, but then I was looking at the point of intersection and then plotting another line there. I think that's why I got the mistake. I've learned from that.
Correct. Let's go to another question. So this is another one. You have z function. Again, it's a maximization. Okay, and here you have 3x1 plus 2x2 subject to x1 minus x2, 0, and then x1 comma x2, 0. What is this irregular type? Is it multiple optimal solution, infeasibility, unboundedness, redundancy? What is happening right now is that you are expanding your mental gymnastics. You are thinking. Wow. 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 Wow.
Hello.
Yeah. Wow. What is your problem?
I'm not hearing. I'm not hearing a thing. So I thought the network was down or something.
This thing has been put on the screen for you to find which irregular type it is. Or you were not here.
No,
You went.
the line somehow went dead. So the reason I said hello just to see if the
Okay, well, you're working, right?
yeah.
Mark, should we send it to you?
Yes, send it the same way you send the first one. Wow. Wow. I'm waiting for all of you. You have just 1 minute. Albert Ben Susan, are you here?
Yes, Doc, I'm here.
Oh, but sure. We don't hear from you, but you are there.
Yes.
You are defined as Abrewana now who is watching. All right. I can see some are struggling. There's no doubt about that. Those who have not provided the answer. Normally that is it. So the answer to this is unboundedness. Unboundedness. And I can see that Emily and Albert got it. So Albert, explain how you think this is unboundedness.
Okay, so first, I think the first thing that I realized is that the operator for the constraint is a greater than or equal to function, which means that when I draw the graph from the point 0, it goes towards the positive infinite space, and that was the only constraint. So that's how I came by the unboundedness.
Yeah. Well, you brought a graph into the picture. Anybody without talking about the graph?
Okay.
Okay, so Doc, without the graph, when you look at the equation, you are going to get x1 is equal to x2. And so it can just keep on. If x1 is 10, x2 will be 10. If x1 is 20, x2 will be 20. There's no cutoff. Any number can fit.
So that constraint, which is x1 minus x2 greater than 0, when you move the x2 to the right-hand side, it will mean that x1 is greater or equal to x2. So that's what she was talking about. Both of them, the non-negativity constraint is there. So the feasible region extends. Right? Like you said, it extends very, very infinitely in the positive direction. It's positive. It's still a feasible solution, okay? But the z function is going to be infinite. Okay? The objective function is going to increase and increase without limitation. You don't understand x. Next one.
Doc, please, can they help me with the graph?
And what?
To explain why it is unbounded.
You want the graph that explains why it's unbounded?
Yes, please.
Okay. So if you have x and y like this, x1 is here, x2 is there. Okay. And we said that the x1 is going to be greater or equal to x2. So if it is equal to, let's take the equal to, the limiting case. It means that if x1 is 10 here, x2 here is what?
10.
But do you know what that means? If x1 is 10, or if it is 0, okay, and like it was before in the question, because like it was before, it was x1 minus x2 greater or equal to 0.
Yes.
So if x2 is 0, x1 is also 0, isn't it?
Yes.
If x2 is 10, watch it. If x2 is 10, then you're going to move this 10 to the right-hand side. So x1 will also be 10, isn't it?
Yes.
So it means that x2 is 10. So if x2 is 0, x1 is also 0. So start from here.
Yeah.
If x2 is 10, x1 is 10. That is also there. Okay. And so at 0, I'll go horizontal. And at this one, so I'll go, if it is 10, 10, I'll go this way, 10, and I'll go that way, 10. You get the point? Now we are looking for a minimum portion. Okay, if we are looking for a maximum portion. So I need to now draw the objective function. If you can remember, the objective function was z equals to 3x1 plus 2x2. So if you want to draw the objective function, take any number. Let's say the number is 6. So z is 6. So if z is 6, okay, now what is x1 if x2 is 0? If x2 is 0, x1 will be 2 because it will be 6 divided by 3. So that will be 2 here. And then if x1 is also 0, x2 will be 3. Okay?
Yes.
So you have 2 here, you have 3 there. Okay. Now we have been able to create a line. We can join this to create the isopropyl line. And then if you want to parallel shift it, you want a place where it will be the last place to leave the feasible solution area. It's not leaving. It's not living because here it's all feasible solution. Now, the common area is between these two. This area is the common. Okay. This is outside. This is outside. This is a common area. And between this common area, it's not closed. It's unbounded. It's opening.
No.
So the Z function will keep shifting out, looking for a place it will hit, but it's not hitting anywhere.
Okay, doc.
Now let's look at one more. Oh, this one is killer. Oh, this is killer. Let's try this. So you have, this might be the last one. Z equals to 5x1 plus 4x2. These are exam questions. 4x2. And then you have x1 plus x2 less than or equal to 10. Okay, x1 is less than or equal to 8. x2 is less than 7. x1 plus x2 is less than or equal to 12. And then finally, your non-negativity constraint. What irregular type of linear programming is this? What irregular type of linear programming are you seeing here? This one, I want a smart person to give me an answer. I got to one person with a solution sent to me. Who is bold? Jerry, are you here? Jerry,
Doc,
are you here?
please, I'm here. I stood up a little. I'm back.
I'm not feeling you at all.
Doc, I stood up. I went to the washroom. I visited the washroom, so I'm back.
I'll be bringing this thing now to physical environment for all of you next week. That one, you're in front of me. So I will know that you're going to wee, isn't it?
Yes, Doc.
All right. So Emily is the only one who has given me an answer. Unfortunately, that is wrong. So the answer to this one is
Redundant.
it's a feasible redundancy. It's a clear redundancy. Why? I mean, you look at the constraints you start drawing and you feel it. Some constraints are not, for example, look at the constraint x1 plus x2 less than or equal to 12. That constraint is redundant. Do you realize that? Yes. I don't know which of you drew it. If you draw this, you see that this guy is a redundant constraint. We don't need him. Because you are telling me that if x, x2 is 0, x1 is 12. If x1 is 0, x2 is 12. Meanwhile, you have already had a similar one here. X1 is 10, x2. So this 10 one, it doesn't make this 12 useful. Every point which is satisfying the 10 one, okay, automatically satisfies the 12 one. So we don't need the 12 one. If you remove that equation I've circled here, it doesn't change the feasible solution region. It doesn't even change the optimal solution. So if feasible solution exists, then we don't need that constraint with the 12. It's a redundant constraint. Who got it? Who got it? It was tough.
I can see it in my graph.
That's your hand. You aren't sure you got it, which means you didn't get it. All right, let's go to the last one for today. I don't want to bore you with the next topic. Next time, we'll model the whole thing in Excel. And we'll also use the simplest algorithm. Okay. But let's look at the very last one. I don't know what some of you were magically doing. I think somebody was magically probably thinking that, oh, since we have done multiple optimal solution and we have done and then unboundedness, then this second one, this one should be feasibility. If that's your mind, oh boy. Oh boy. Oh boy. That is not how we are going. Use the analysis and then let's get it. So this is the last one. Be careful about it. So this is z equals to 2x1 plus 3x2. Subject, this is the last one, x1 plus x2, 8, x1 plus x2, 4, x1, comma x2, 0 positive. This is the last and the easiest.
Infeasible.
Please write your answer down. We are not talking in Wakola. You never even spoke about any of the results. Now this one there, you are speaking about the result. What changed? I said you should type your answer down. I didn't say you should say it. The reason why I'm giving you these things is because I want you to master them, because you're going to have multiple of these. Manya, 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 manya. So you wouldn't want to say that, oh, I didn't know how it works. Now, by the time you have done 4, 5, 6, you should have mastered the thing. Okay, so this is infeasibility. Emily is the only one who sent a correct answer. All of you sent wrong answers.
So I sent infeasible.
Okay. Emily, explain why it's infeasible.
Doug, because one of the constraints is saying is greater than 8, and another is saying is greater than is less than 4. So the two are not going to meet.
That's it. They will never meet. Infeasibility, okay, is an issue. All right. So guys, that brings us to the end of irregular types of linear programming. It has been an interesting discussion. Yeah.
Please, before we end, can you quickly take us through the question you asked at the beginning? Because I'm not sure myself. You were asking about what happens to the decision variable when it's in maximum optimization if it becomes minimum. I'm not too sure myself. Can you please take us through?
Okay, so in a minimization, the decision variable, how different is it in a maximization?
Yes.
Was that a question I asked?
Yes, Doc, you were asking what becomes of them when they go to the other side. So what becomes of the decision variable when the problem becomes a minimization problem?
Well, that wasn't my question. That wasn't a question I wanted to ask, actually.
Doc, you said the
I
available
think the
resources
question was,
what did they become
the-
in a maximization? That was the question that you asked.
The decision variable play exactly the same role in both minimization and maximization.
the question was, when minimization is not possible, what happens to the maximization?
Yeah, people confuse me more. Emily, back to your question. There is no difference. The decision variables play the same role.
Yeah, because Jerry gave an answer that they become available resources, and he said yes. So I got confused.
Who said available resources?
Jerry provided an answer when he asked the question.
That is wrong because the question was not about that. I just realized the question was more about a primal model and a dual. And then when you said you have treated the two, I thought you have done the primal and the dual. Because in the minimization, we explain the concept of complementary slackness theorem, and why you connect the primal linear programming with the dual linear program. So I was asking that if the primal is unbounded, then the dual, if the primal is infeasible, the dual is unbounded. So I was asking that what becomes of the decision variable if you were in a primal model and you move to a dual? And apparently, I don't think you've treated that, have you?
No, Doc.
So that was a question I was asking. So it has nothing to do with the one I asked on minimization, maximization. So Jerry, that point you were saying, you were also answering a wrong question. And because in my mind, I thought I was asking a question on duality. We'll look at duality next time.
Oh, so that is under primary duality, right?
Correct.
Okay, thank you.
Okay, so let's go back to what you did.